Hello there, Mr. Sutton here with the BC Calculus 8-4 Extra Practice Number 1 Solutions on Vector Free Response Practice. On this problem, the curve C in the xy plane is given parametrically by x and y, where the derivative of x is this function and we have y prime over here as well, between 1 and 6. Alright, so we want to find the slope of the line tangent to C at the point where t is 3. So for doing tangent line slope, we're going to use our parametric derivative formula, which means dy over dx is going to be y prime over x prime, specifically y prime of 3 over x prime of 3. So we're going to put these in the calculator and crank that out. So on my calculator, I've got x prime entered in the y1 function here, and y prime I'm going to use y2 to represent that one. So let's quit back to the main screen. And let me do, let's see, alpha y equals to get my fancy fraction. I need to do y2 of 3 over y1 of 3 based on where I stored things. So y2, and let's do alpha trace to get that. So y2 of 3 over, now we do alpha trace y1 of 3. And press enter to get negative 0.230. On this problem, we want to find out between the intervals 1 and 6, what is the value of t where our line tangent to C is vertical. So if we have a vertical tangent line, that means there is no left-right movement, which means x prime needs to equal 0 at that spot. So let's set x prime equal to 0 and solve that on the grapher. And then whatever values we get out of there, we're also going to test in y prime just to make sure we have some vertical movement versus just the thing being at rest. So on my calculator, in y equals, I'm going to deselect y2 because I don't want to graph y prime. And let's see here, we had the interval from 1 to 6. So let me do window for this thing. And 1 to 6 it is. Let me zoom 0 this. So here is our x prime. And we see that it does in fact equal 0 in one spot right here. Let me do second trace to find out what that spot is. So 0, option 0. Let's press enter a little bit to the left, a little bit to the right. Enter one more time. That comes out to about 4.7124. I'm going to store that as A, both on the paper and on my calculator. So let me immediately go back here, quit out, and store that as alpha A. All right. Now that I've done that, I need to actually plug this into y prime just to make sure I don't get another 0. Because again, if I get another 0, that means we're at rest, not vertically tangent. So let's see here. Let me go to alpha trace and then y2. That's my y prime. Let me plug in A, so alpha A. And pressing enter, we get about 0.744 and some change. Now, significantly, this is not 0, which means that we do indeed have a vertical tangent line at time A. For this problem part, we want to find the length of the curve C on the interval from 1 to 6. So for this one, we basically need the arc length, and for that we're going to need the derivatives of the thing that we're taking the arc length of. We have x prime right here, we have y prime right here. So we just need an integral then from 1 to 6 of, now we're just going to need, since this is parametric, we use the parametric arc length setup. So we have the square root of dx over dt squared plus dy over dt squared. And let's just plug that in the calculator. So here's what that looks like on the calculator. We have integral 1 to 6. Here's x prime squared, and here's y prime squared. Press enter on all that. And we get a grand total of, well, we're making the calculator think on this one, about 10.569. For this last part of the problem, given that y of 1 is 2, they want y of 3. So this is a fairly straightforward problem for a part D on these. We have just the fundamental theorem we need to use here. So we can say that y of 3 equals our initial value of 2 plus Now, if I'm going from time 1 to time 3, I need an integral from 1 to 3. An integral of the change in y, so y prime, which is already defined up here, but we'll write y prime here. And now for the calculator. So integral from 1 to 3, y2 is where we stored y prime. We still have that initial 2 that we're adding in there. And pressing enter gives us about 2.805. And we're done. On this free response problem, which is calculator-based, we have a particle moving in the xy plane. We have the parameters x of t and y of t, which they're not spelling out for us, but they did give us x prime and y prime over here. And they're telling us at time 0 the particle is at 1, 2. And oh, by the way, here's the path of the particle. It's a nice little hand-drawn graph here. So we want the position for part A, position of the particle at time 2. In order to get this position, I need the starting value for x and y, which they gave us in this point here. And we're just going to use the fundamental theorem on each of these to figure out the new position. So let's do the x's first. We're looking for x of 2. That's going to be your initial x value at 0, which was 1, plus an integral from, let's see, we're going from 0 to 2 of, we'll say x prime of t dt, because x prime's already defined up here. Now we're going to need the calculator. To make my life a little bit easier, in my y equals, I'm going to put my x prime as y1 and my y prime as y2, so I don't have to keep rewriting them. And then let's quit out of there and just do a little FTC action here. So we have 1 plus math9 integral from 0 to 2. And for x prime, we're going to need, let's see, alpha trace y1 dx on the calculator at least, dt on the paper. Comes out to about 1.461. Now to do y of 2, it's the same kind of setup. We're going to need that initial y value, which was 2 based off that point. And let's see, we have the integral from 0 to 2 again, this time of y prime of t dt. Let's go back to the calculator for that. My setup is pretty similar. I'm actually going to yank my input from before, and I'm going to change this initial value here to a 2. Still have the same integral limits, but now I need y2 instead of y1 because I'm dealing with y prime instead of x prime. And press enter on all that. About 4.268. So that means we have a position of this, comma, this, and we'll call it a day on this one. For this problem, we want the slope of the line tangent to the particle's path at time 2. So for parametric slope, we're just doing y prime of 2 over x prime of 2. And we've already got those defined, so we just have to plug that in the calculator. To do this on the calculator, I'll just do a fancy fraction here. We've got y2 of 2, that's y prime. y1 of 2 was x prime. Press enter. And that's about 8.555. For this problem part, they want the speed of the particle at time 2 and the acceleration vector at that same time. So for speed, we're doing square root of x prime of 2 squared plus y prime of 2 squared. And we already know x prime and y prime, so we can just put this directly into the calculator. Here's what that looks like on the calculator. Here's x prime of 2 that we're squaring, and we're squaring y prime of 2 right here. That gives us a total of about 5.630. Next, for the acceleration vector, we've already got velocity, so we have to do acceleration by doing the derivative of x prime and the derivative of y prime, so x double prime of 2 and y double prime of 2. Since we already know x prime and y prime, we can take the derivative of those functions at a specific point without actually showing what x double prime and y double prime look like algebraically. So let's just take the derivative of those on the calculator now. Here's the setup for x double prime of 2. I'm just taking the derivative of x prime, which again I've stored in y1, at the x value 2, or the input 2 anyway. It's a t value, I guess. So enter on that. It's about 3.027. And now we'll do the same for y double prime of 2. So I can actually steal the input from earlier because it's almost exactly what I need. The only thing I need to change is that instead of y1, I want y2 because that's where I've stored y prime. So alpha trace put y2 in there, still evaluating that at the input 2, and that comes out to negative 24.911. So there's our acceleration vector. For part D on this one, they're asking us to consider a rectangle with vertices at 0, 0, x of t comma 0, x of t comma y of t, and 0 comma y of t for time greater than or equal to 0. And then we want to know between times 0 and 2 at what time is our perimeter of the rectangle a maximum. Okay, so let's get a visual of what's going on. We have this rectangle, and this is where this visual up here is kind of helpful. We have a vertex at 0, 0, and then the kitty corner somewhere on this curve. So we have something essentially that looks like this. And now we're trying to figure out how to maximize this rectangle's perimeter. So just to label the sides a little bit, we know that this base here and this top side as well, this corresponds with x of t. That's your x value after a certain amount of time. And vertically, we've got y of t. So we can write the perimeter then, which I'll call p of t, as 2 times x of t plus 2 times y of t. And now to find the way to maximize this, I need to find the derivative of this, p prime of t, which is just going to be 2x prime plus 2y prime. Now I need to figure out critical values for this, so let me just set this equal to 0 and solve that on the calculator. To do that, I'm going to go to my y equals, and I've entered a third function in here. This is essentially 2x prime plus 2y prime, because I already had x and y prime in y1 and y2. I'm going to graph this in a sec, but let me deselect x and y prime, because I really don't care what their individual graphs look like at this point. And now let me go to Window, and I want to graph between 0 and 2, so let me enter those for my x-min and x-max, and then we'll do zoom 0, zoom fit. And we want to figure out where this thing crosses the x-axis now. So this is p prime we are graphing. So it's going up a little bit. Is it coming back down? It is. There we go. There's our x-intercept. So let's go ahead and figure out what this spot is right here. So second trace, option 2 for zeros. We're a little bit to the right here. Let me just move my spider a little closer. So we enter, press enter again. One more time for fun. And that comes out to about 1.722. So there it is again. And I'm going to call that time A, just so I don't have to keep rewriting it. So now I have to prove that I've got a maximum somewhere here. One way you could do this is with the candidates test. We could actually plug A and also the endpoints 0 and 2 into this p function that we just created. And I mean, we could do this on the calculator, but it would be kind of annoying because you have to calculate x of t and y of t, and those aren't explicitly defined, so you would have to use an FTC for each of those. Kind of annoying. Another way to do this is to realize that since we've only got one critical value and it's a local max, we can very quickly justify that it's an absolute max. So we would say that p prime is greater than 0 on the interval from 0 to a, and p prime of t is less than 0 below the x-axis on the interval from a to 2. So basically then, the perimeter is increasing until we get to time a, and it's decreasing after that. So a must be our absolute max. So we have our max perimeter then at time a. On this problem, we have a particle moving in the xy plane on time 0 to 8, and here's the position vector. For the first part here, they want the speed of the particle at time 2 with units of measure. All right, so I'm going to take a minute and enter my x of t and y of t in the calculator because there's a chance, so I've got them entered in my y equals. y1 is x of 2, y2 is y of 2. There's a chance I'm going to be using these again. And for this problem now, if we want the speed, then I'm going to be doing essentially the square root of x prime of 2 squared plus y prime of 2 squared. So I could do those derivatives directly on the calculator since I'm just taking the derivative of a function that's already defined at a specific point. I don't have to show what x prime and y prime are. It turns out I'm actually going to show what they are anyway, though, because I'm going to be using them specifically as functions later on in this free response. I've just kind of read ahead, which is always a good idea, and I know what I'm going to need. So let me define x prime now, as this is going to be derivative of sine of 2t, so 2 cosine of 2t. And y prime I'll define as 2t minus 1. And let me put those in the calculator as well. So I've got those entered as y3 for x prime and y4 for y prime. All right, now again for speed, this one I didn't really need these predefined derivatives, but I've got them now. So I can just do the square root of x prime of 2 squared plus y prime of 2 squared. So here's what that looks like on my calculator. Again, I defined x prime as y3, y4 is my y prime, and doing it this way, instead of doing like derivative of y1 evaluated at 2, it just saves me some bulky derivative notation. Other than that, I could have done it the other way. But this comes out to 3.272, and that's in meters per second. They gave us units, so we're giving them units back. Speed is a meters per second unit, so there we are. On this part of the problem, they want to know at time 4, is our speed increasing or decreasing? The fastest way to figure this out is to take the derivative of speed, which we can define a function for. I mean, we just found the speed at a specific spot on the last part of the problem. So take the derivative at a specific spot and figure out if that's positive or negative. So in general, this speed expression, that's the square root of x prime of t squared plus y prime of t squared. So I'm going to take the derivative of this expression evaluated at time 4. Let me do that on the calculator now. And I don't actually have to spell out what this function looks like, what the derivative of this function looks like anyway, because I'm just taking its derivative as a specific spot. So here we go. Here's what this looks like on the calculator. So we do math 8 to get derivative. The inner function that we've gotten here, this is the square root of x prime squared plus y prime squared, evaluated at 4. And in order to get credit for this, I did need to define what x prime and y prime actually were, because otherwise we have no way of knowing. So pressing enter on this now, we've got 2.163. That is most importantly a positive number, greater than 0. So that means that our speed, whose derivative we just found, must be increasing at time 4. For this part, to find the total distance traveled from 0 to 5 seconds, we basically need the integral of speed over that period. So integral from 0 to 5 of pretty much what we just took the derivative of, square root of x prime squared plus y prime squared. And this is going to be a dt kind of setup because this is all in terms of time. So there's the setup on the calculator, and at this point I'm kind of wishing I'd created a speed function on my calculator because we seem to be using it over and over again. Enter for this, and that integral is going to give us a total distance value of, drum roll please, about 22.382, and that's going to be in meters. For this last problem part, at time 8, the particle begins moving in a straight line. And for time greater than or equal to 8, it's traveling with the same vector velocity, velocity vector that it had at time 8. So basically, the x prime and the y prime are constant after you get to 8. Based off that, we want the position of our particle at time 10. So one way you can think about this is essentially like using a tangent line approximation to figure out the particle's position, only it's the particle's actual position happens to be what a tangent line approximation would have been. So because of this, I'm going to use my general tangent line setup. I'm going to say f of x in general is equal to f of a plus f prime of a times x minus a. So this is essentially taking a fixed slope, this f prime of a, which we're going to calculate at time 8 for x and y. And you've got wherever you were at time 8, that's this f of a part, and then we've got x minus a, so you're basically plugging in 10 for your x value and doing 10 minus 8 both times. So for the new x value then, we can say x is going to equal, now where were we at time 8? Well, I don't know, but we have a function, x for telling us where we are at any time. So I'm going to write x of 8 plus x prime of 8, and I've got these already defined, so I can just plug it in my calculator. And then this is going to be 10 minus 8. So let's use the calculator to see what that is. So here's the setup on the calculator. X of 8 is just y1 of 8, because that's where I stored x of t in the very beginning of this problem. X prime, that was y3 on my calculator, and I'm plugging 8 into that as well. And I'll trust myself to be able to successfully do 10 minus 8 without the calculator's help. So let's see. Enter on that, about negative 4.119. Now we're going to do the same thing to find y of 10, because we need the y value for the full position of our particle at time 10. So that's going to be y of 8 plus y prime of 8, and still have 10 minus 8. Going back to the calculator, I can actually pull my input from earlier. I just need to change a couple things. For example, instead of y2, or y1 rather, I want y2, so alpha trace y2, because that's where I stored y of t. And instead of y3, I want y4, because that's where I stored y prime. Everything else is exactly the same. So enter. Gives us exactly 86. Hey, what are the chances? So my full position then, negative 4.119, 86.